Hello and welcome back. Today we are going to do more true trees. Yay! In the last video we went through some basic problems. So now today we are looking for more complicated and advanced true tree problems. Let's dive into it. This is our fourth problem, and as always, we are going to convert everything into and or statement. Okay, so look at our first premise. This is logically equivalent to not P or parenthesis Q or R. All right, and then take the negation of our conclusion, which is right here. Okay, the negation of this statement, P if P then R. Okay, first let's convert P if P then R into and or statement. We have not P or R. So the negation of this is not B or R, and then a big negation up here. All right. According to De Morgan's law, we have something like this. Not P and not R. All right. I'm gonna put De Morgan's law. All right. Okay, let's come back to this one. So this one is equivalent to not P and not R. Okay, so now not P is logically equivalent to P. So we can rewrite this statement here as P and not R. That is our negation of the conclusion. Okay, so now we're gonna set up the truth trees. All right. Since we have an and over here, we will stack our statement, right? Okay, first line of tree. P, stack it up, not R. All right, so now look at our second line of the tree, which is the first premise. We have not P or this group, Q or R. All right, so we're gonna split it out into two branches. All right, we have not P on the left, and this group up here we have two variable. So we split it out into two sub branches. Okay, so we have we have Q or R. All right. Is there any contradiction? Let's consider this branch first. There is a contradiction. We have not P and P in the same branch. All right, so this branch fail. Therefore, it is closed. Okay, how about this branch here? We don't know yet, right? We have different variables. So we don't know if it's closed or open on this one yet. Okay, our last branch. Is there any contradiction? There is a contradiction. We have R and not R in this branch. Therefore, this branch is failed and it is closed. Alright, I'm gonna erase these lines for better visualization. Okay, that's all I can have. Sorry, y'all. Okay. Let's see. Up here we have not Q is our third line, which is the second premise. And we're going to stack it up, right? Under this branch. We have not Q. Alright, go ahead and see if there's any contradiction in this branch. Yep, there is a contradiction. We have not Q and Q. Therefore, this branch is also failed. And it is closed. Okay, by this, we know that there are contradictions between our premises and the negation of the conclusion. We can jump to the conclusion that the original statement, the original argument here is valid. This is our last problem from the topic, and before diving into the problem, I just want to say it is important to practice and have the ability to break down a problem into steps. By analyzing and going through each step, you can actually, it's actually really easy for us to see the solution to solve the problem. Alright, that's enough yapping. Okay, so now let's do the problem. Okay, this problem, we have the conclusion contains the biconditional of P and Q. What does it mean by the biconditional of P and Q? It states for P if and only if Q. So from this statement, it is true if both P and Q have the same truth values. For example, P is true and Q is true, or P is false and Q is false. But it is false if P and Q have the opposite truth values. For example, P is true, Q is false, and vice versa. Alright, so we're gonna convert this conclusion into an or and statement. Okay, so we have S and if and only if Q is logically equivalent to S. If S, then Q. And if Q, then S. All right. And this statement is logically equivalent to not S or Q, and not Q or S. All right, that is our and also or statement for the biconditional of P and Q. And then we're gonna do the negation of this statement, since is our conclusion. Negation of S if S and if and only if Q. Okay, I'm gonna use white. We're gonna rewrite the top statement, not S or Q, and not Q or S. And then a big negation on top. All right. So now we're gonna break it down using De Morgan's law. First, we need to know the order of disjunction. So we're gonna solve for the negation first, and then or. All right? Okay, we have, let's name this one A and B. So we have something like A and B and then the negation of this, right? By the De Morgan's law, this is logically equivalent to not A or not B. Okay, let's do this down here. Okay, so we have not S or Q, and then the negation, or Q, not Q or S, and then the negation. All right, so now we still have the negation, and of course we need to break down the negation. Okay, so we have not S and Q, not Q, sorry, or not Q and not S. Okay, so not S is just S and not Q, or Q and not S. All right, this is our negation of S if and only if Q, sorry. All right, let's also convert this first premise into and or statement. This is logically equivalent to not P or Q or R. Okay, we label it at first, second, and third. Okay, let's draw our tree. Okay, since we have the R in the middle, this branch is gonna split up like this. All right, this statement here, we have S stacked on Q. And also the second one, the same thing. Q is stacked on not S. Okay, that is our first line of the tree. Okay, our second one is not P or Q as a group or R. Okay, so we're gonna split up these two like this. Okay, we know that this one is R, this one is R, but we have this one as a group, so we're gonna have two sub-branches like this. Not P or Q, not P or Q. All right, let's see if there is any contradictions. Okay, I see this branch over here has a contradiction. We have Q and not Q. So this branch is failed. Oh, it turned into red. Failed, therefore it is closed. Okay, how about the right branches? Is there any contradiction? No, right? Okay, but we see this one. We have Q and up to Q on the top. There is no contradiction, but we didn't go over all the premises yet. So we cannot conclude this branch is open until we go through all the premises. Okay, so let's hold on into that. Okay. Let's consider our third line, which is the second premise, or S. Okay, we have two branches, or S. And then or S, or S. Also this one. Okay. Is there any contradictions? We have a contradiction on this line, right? We have S at the bottom, the very bottom, and then not S at the very top. Okay, one more. We have this line here. Oh my goodness. There, right? We have S at the very bottom also, but we have not S on the top. Okay. Is there any open branches? There is, right? We have this branch clearly. We have Q on the bottom and on the top. Wait, hold on, I see a problem. It's failed at the very bottom, which is S and not S, right? So this is also failed, closed, fail, closed, and fail, therefore closed. Okay? But this branch here, we see R at the very bottom, up to R. So there is no contradiction here. Up to not S, up to Q. Therefore, this branch is open. Okay, remember from the last video, I said if you find just at least one open branch, there is a possible chance that all the premises are true, but the conclusion is false. This one is the case. At least one open branch, we can conclude that our original statement here is invalid. Okay, so that is what we have for the truth tree. I hope you guys enjoy these videos and have kind of like some idea about how to draw a truth tree. And please wait for more math contents coming. Thank you.